Okay, welcome to fluids. This is new stuff, and this video is going to be a little on the long side, but it's important information, so stick with me. Fluids, we got to start with states of matter. This should be really familiar. We've got solids, liquids, and you guessed it, gases. Those are three states of matter that we care about. There's plasmas and a few other things that we just don't have anything to do with. Um, so these are the three we're going to focus on. Now, what are fluids? Fluids, liquids, and gases are easily deformed by external forces. In other words, they do not hold their shape. So liquids and gases are both considered fluids. When you push down, here's an example. When you push down on memory foam, it leaves an imprint that eventually returns to its previous shape. That's a characteristic of solids, that if they are deformed, they don't lose their shape. When you push on a liquid or gas, it moves the molecules and they do not ever return to their previous position. So if you get steam or gas or something and you move your hand through it, it's gone. You push it out of the way and it doesn't return. Okay? Water. You put your hand in the water and it pushes the water out of the way, and even though it might fill in behind, it'll be other molecules that are taking the place. The water doesn't return to its previous shape. Okay, fluids are considered incompressible, which means that they have a fixed volume that doesn't depend on the container. For example, if you pour a liquid from a test tube, a narrow test tube, to a beaker, a wide beaker, the volume of the liquid does not change. That's pretty straightforward, that it doesn't matter what shape the container has, the volume of that liquid is pretty much fixed. That's what we mean by incompressible. Static. The definition of static is not moving. You know, static versus kinetic friction. Static is motionless. So hydrostatics is the study of fluids at rest. And I put a little star here because it's important to understand that the molecules in that fluid do not stop moving. And the collisions of those atoms and molecules in a fluid creates fluid pressure because pressure is a part of what we're doing. So basically we're studying fluids at rest, um, but the molecules, the movement of those molecules, the vibrations of those molecules is something of importance for us. Static fluids exert a force perpendicular to the surface. So wherever you are in that fluid, there is a force perpendicular to the surface. Now you probably already know that pressure, average pressure, is force over area. So I'm going to kind of do this clockwise. So average force or average pressure is equal to force over area. This is it in words. Pressure is a scalar. It's not a vector, it's a scalar because molecules move in random directions. So when those molecules are vibrating, it's random. And so you can't say that pressure has a specific direction because the molecules are going in many directions. Okay, now the other thing I want to point out here is that there are lots of P's on your equation sheet. There's pressure, there's power, there's momentum. But the nice thing about the equation sheet is that all of those equations are grouped by topic. So there's Newtonian mechanics, there's electrostatics, there's fluid dynamics, fluid and thermodynamics. So, you know, depending on the situation, you can go to that section of your note sheet and know that that's the P you're talking about. Just something to consider. Okay, the units of pressure, because it's force over area, it's newtons per meter squared. Now, we basically named that after Pascal, Blaise Pascal, so it's capital PA, which is a dead guy unit. For those of you who didn't have me last year, every time we capitalize a unit, it's named after a dead guy. Of course, the exception to that is the Curie, which I think we get to later in the spring. Okay, which is named after a dead lady. Another common unit that you'll see is the atmosphere, ATM, which is defined as the average air pressure at sea level. So on your equation sheet, and this is an important thing to pay attention to. On your equation sheet, on the inside cover, it says 1 atmosphere is 1 times 10 to the 5th pascals. That's the value that is on the AP exam. That's the value that you'll be using to calculate stuff in the AP exam. Your book gives a different um, ratio. Your book says that one atmosphere is 101.3 kilopascals, which is slightly different. So if you're doing problems from the book, practice problems, the answer will be slightly different. It's not going to be exactly the same. So you just have to recognize that um, that the AP equation sheet is a little more generous in terms of rounding, and the book itself gives you a more exact number. It's like the difference between 10 and 9.8 for gravity. Okay, Pascal's principle. A change in pressure at any point in a confined fluid is transmitted everywhere throughout that fluid. This is important. The typical problem or the example is the hydraulic lift. I don't know why I'm going to try and draw this. So let's say you have a car, and yes, it's a very box-like car that I've got here, and I'm going to put it over some huge cylinder here, and over here I'm going to put a very narrow cylinder, and this is filled with fluid. Just fluid here. Let's just assume that it's all there. Now, on either side is a piston. So we've got a piston here. Basically, it's a narrow tube with a piston, and then a big area here with a piston. And so what happens is when you apply a force here, you've got some force in some area. Let's call it F1 and A1. That pressure is the same over here, where we've got F2, A2. Well, here's the thing, that if my area goes up, the force applied goes up because the pressure has to be the same. And that's how we're able to lift really heavy cars with something like a hydraulic lift. So you've got a confined fluid, and if you apply a certain pressure over on one side, that same pressure is acting on the other side. And so the biggest difference is that you're widening the area, and so the force has to increase to maintain the same pressure. All right. You can look on page 321 in the book for exactly how a hydraulic lift operates, but it's pretty much this. Okay, density, which should be somewhat familiar. Rho, the Greek letter rho, is equal to mass over volume, and the units of density are kilograms per meters cubed. And that's really all you need. I mean, you should know that already, so I don't need to go into a lot of detail. It's how much stuff per unit volume you have. Um, Now, one interesting note that I probably should have written down is that water reaches maximum density at 4 degrees Celsius, which is really interesting. I mean, it's as far as I know, it's the only substance that does that. Everything else that I'm aware of, there may be exceptions, but everything else I'm aware of reaches its maximum density when it's a solid and not when it's a liquid. And this is really why ice floats, because ice has a lower density than water that's at 4 degrees Celsius. Okay, just a little side note that you may want to think about. Okay, pressure below the surface. So divers or submarines or submersibles, um, as they go deeper and deeper, if you have ever seen a submarine movie, you know the deeper they go, the more pressure there is on the submarine. Divers have to deal with pressure because if they come up too fast, then I think it's called the bends. So that pressure changes as you go deeper and deeper. Now the reason for that is gravity. So if I have over here a cup filled with liquid, what happens is the molecules at the bottom of that cup are under more pressure because of the molecules stacked on top of them. The atmosphere is another one. As you get higher and higher and higher in the atmosphere, there are fewer and fewer molecules because everything kind of stacks up, and the stuff on the bottom gets squeezed more than the stuff that's up on top. And so pressure below the surface is due pretty much to gravity pulling those molecules down. And so it's denser on the bottom, more pressure on the bottom because of gravity. Now, this equation is used to tell us the pressure below the surface. So P, the pressure in the fluid, is equal to atmospheric pressure, 1 times 10 to the 5th pascals, plus the density times the acceleration due to gravity and the depth. They use H for depth. Um, in the book, I think they use the letter D. In your equation sheet, it's H, and I'm going to go with the equation sheet on this one. Now, this is assuming that the surface of the fluid is open to the atmosphere. So, if you're talking about, let's see, here we are, here's your submarine. The surface is exposed to the atmosphere, and so that's the thing. Um, okay, let's move on here. Now, in some cases, it may be easier to find the change in pressure. That's referred to as the gauge pressure. Okay, the gauge pressure is that change in pressure. It's the difference between the pressure of the fluid and atmospheric pressure. Okay, and so the change in pressure is rho times G times H, which, you know, isn't that hard to figure out. There is an example problem on page 325 and 326 that deals with this type of situation. You should probably check it out. And Ninja Squirrel Productions. Now the video, this is almost 12 minutes long, which I'll be honest with you is I was worried that it'd be a little longer. So next up we're going to deal, not today, but the next video is going to deal with buoyancy and Archimedes principle and a few other things there. So we're moving. Thanks.